Okay, 2012 Waves for Level 3. Question 2, the Doppler effect. Jess and Tom have identical horns that both produce a frequency of 420 Hz. That's important. Tom stands beside the road listening to Jess sound her horn as she rides away in her car. The speed of sound in air is 343 meters per second. Calculate the Doppler shifted frequency of the horn as heard by Tom when Jess is travelling away at 12 meters per second. That's also important. Okay, so this is using the Doppler effect equation. And we're after the frequency, so F dash for the Doppler shifted frequency is equal to the actual frequency times by velocity of the wave over velocity of the wave plus or minus velocity of the source. So we've got the speed of sound, which is the velocity of the wave. We've got the frequency, and we know the source is moving 12 meters per second. Now the only thing we don't know is whether to use plus or minus. So I always go back to an observation of reality for this, and I remember that a Formula 1 car goes from a high to a low frequency, going as it comes towards and away. So it's going to be lower when it's going away. Okay, so we just have to work out whether a plus or a minus will give us a lower going away. So for F to be lower, so for F to for F dash to decrease, we have to take F times by something that is a number, we'll call it X, which is less than 1. So the VW over VW plus or minus VS must be less than 1. The only way for that to occur is if we add VS onto the bottom. So we end up with a number bigger than VW on the bottom, so that VW over VW plus a number bigger, VW over a number bigger than VW is going to be less than 1. So if we were to do that, we would just say it's going to be 420 times by 343, look at that, it still works, divided by 343 plus 12. And when you plug all those numbers in, you end up with 406 Hertz is the apparent frequency that you would hear. B. Jess's car changes to a new steady speed, so we can't rely on the previous information for velocities and such. And then Jess sounds her horn again. Tom sounds his horn too and notices beats. Okay, beat frequency. That's our big concept to be aware of. Explain the phenomenon of beats. Your answer could include what beats are, why beats form, why the beat frequency is the difference between the two incident wave frequencies. Okay, so you can take these suggestions as actual, and I would include them. So you'd say what beats are. Beats are the what you would describe the louder and softer alternating, which is over the top of your other frequencies. If you're explaining why they form, it's because they're alternately reinforcing. I'm not going to write this in full because it's a bit hard on here, but you just want to hear what I say. It's ultimately reinforcing, and what's the opposite to reinforcing? Cancelling, I guess. Cancelling or subtracting. As they move in and out of phase. And I guess there's some important things. The waves or the frequencies have to be similar. So this is the conditions of why they form, and so that means they can't be too different from each other, and it's going to be the number of the frequency of the beats, or the beat frequency, or the number of times it beats, is going to be the difference between the two. That's your formula. F1 minus F2, or F2 minus F1, depending on how you look at it. Okay, so now that's points 1 and 2 effectively covered, I think. Check the marking schedule as well, in case I've missed anything. I'm just trying to explain it in a bit more longer form than the answers give. And the last part, why the beat frequency is the difference between the two incident wave frequencies. I'm just going to scoot over to the side here to show you this, because this gets quite tricky, I think. and having a glance through the marking schedule, it doesn't give you a lot of detail, so I'm going to give you the really quick lesson in beats. Again, I'm going to draw two waves on two axes that are kind of over the top of each other. There's one wave, there's another wave, and the beat frequency, as we remember, is the difference, I'm going to call it delta F, between them. So we've got this frequency 1 here, we've got this frequency 2 here. It doesn't matter which one's F1 and F2, it's just how you use it. What we can see here is that our beat frequency, delta F, is going to be F2 minus F1. But just to be more useful, if you like, that's just what you would see in there. This is actually our answer, our solution. But why do we hear it at that? So that's kind of where we're aiming for. So I'm going to start from kind of a point of view here where once F2 cycles through once, okay, until both of those initial points, which I've just marked with asterisks, red asterisks, until they hit at the same time again, remember time is on our axis here, you won't hear a beat frequency. In fact, it's actually the peaks. When the two peaks are matching together, and you get an extraordinarily loud amplitude. But I'll just go from that central point because it makes it easier for our addition here. So what you're going to find is you need to have F2 cycling through a certain number of times, okay, and if I say the starting point of F2, so we're using F2 as our reference point, we need to match up the same length of F2 once again to make our beat frequency beat. This would have been better if I'd started at a positive amplitude, but you could do it from here, and it's still going to be the same delta F anyway, so maybe we'll just go from there. But anyway, so you'll need F1 to cycle through enough parts of it, enough times that it cycles all the way through plus the delta F. So I'm not really saying this very well, but if you just follow me for a while and we'll see how we go. F1, our top frequency, if we divide that by delta F, that's going to give us the proportion or the number of times that we get delta F within that F1 frequency. Okay, and now what we want one more plus delta F. We want one more delta F to make it add up to F2, and that's going to give us our beat frequency. Okay, does that make sense? I can't get an answer back from you, so I hope it does. So if I was to kind of do this strictly speaking correctly, we would multiply F1 by delta F and then divide by delta F plus, and you can see that that's going to give us the same equation up here. Okay, so but what we've done is we've taken F1 divided by delta F gives you the number of bits of delta F that there could be in F1. We have to add one more delta F onto that to add up to F2, and let's see. Oh yeah, that's right. So why do we add this delta F in? It's because F1 over delta F is just giving us a number of delta Fs. Okay, so let's do it like this. The number of delta Fs times delta F plus 1 delta F equals our F2, and that's just using the length of the wave as a way to derive our beat frequency. And so that's, we can write that in a different way, write that in a slightly different way. We could say that F1 over delta F plus 1, and then we just one extra delta F times by delta F equals F2. So let's say that in a slightly different way. Hopefully all of this talking helps it click in your mind as well. So this part, F1 over delta F, is the number of delta Fs that there are in F1, in the original frequency. You add one more to that, and you get the whole number of delta Fs that are in F2. Okay. In fact, you could rearrange this equation, F2 over delta F to find the number of delta Fs in F2, equals F1 over delta F plus 1. So then you can take that equation and that understanding, and you can throw that all the way up into here, and you end up with this. You can rearrange this equation to get that, and that's essentially where it comes from. Okay, should we look on to the next one, see if we need to split it up into a new video? I think we will make that a separate video. No, we don't need to go that far. We'll just launch straight in with our original video on one. When Tom sounds his horn, he hears a beat frequency of 6 Hz. Calculate the speed at which Jess is moving away from Tom. So we've got 6 as our beat frequency, which equals F1 minus F2, if we're being strict according to our equations given us in the right way. I added F2 minus F1, but you have to just be clear which one you're dealing with. So what have we got? 420 Hertz is the sound of them, and if we're considering that Jess is still driving away, that means her frequency will be lower. So Tom is hearing a beat frequency with Jess moving away, so we're trying to find F2. That means Tom's frequency is still 620, so we've got 420 minus F2. If we rearrange this for F2, F2 gives us Jess's frequency of 414 Hertz. Okay, so that's one part. That's the frequency, the apparent frequency that's heard. Now what we'd have to do is plug this into our equation. F dash equals F VW over VW, and we plus it because she's moving away from the earlier one, plus VS. We don't know VS. We know F is 420, F dash is 414, VW is still 343 meters per second, so we're rearranging for VS, and when you do that you'll come up with 4.97 meters per second. Okay, last one. Speed cameras measure the speed of a car by measuring the Doppler shift of the radio signal reflected by the car. Explain why a speed camera cannot measure the speed of the car at the moment when the car passes the camera. Okay, so the main thing is there's no, it's like they're at the same point. If the direction of motion is here, then the waves are travelling that we're actually interested in for Doppler effect shift are travelling in this direction, this plane. And so here's our observer, our F dash here, and this is our F, our source. Within this range, there is no change in wavelength from the source moving towards or away from the source, so from the observer. So yeah, I guess it's not moving away, it's not moving towards. The relative speed in that plane that really matters is 0. This is the plane that really matters. The relative speed between these two at that point in time is 0. That's what you're really getting towards. So the car's not moving away towards the camera. So the car and the radio wave are moving perpendicular to each other at right angles, and that's where we come with the idea of no relative velocity, and the reflected waves will therefore have the same frequency and wavelength. So no change in the wavelength. That's what we're getting at there. Done.